So welcome everybody to Theory Lunch. Um, Today we're going to have Arvind Mahankali presenting, and he'll be telling us about optimal L1 subset selection, and also a faster polynomial time approximation scheme for L1 low rank approximation. So with that, Arvind, you want to take it away?
Hi everyone, thanks for coming. So today I'll be talking about some algorithms for L1 low rank approximation, and this is joint work with David Woodruff. So first I'll give some quick background and overview of the problem, and then I'll go straight to the algorithms. So we'll be presenting two algorithms today. So the original problem of low rank approximation is a very well-studied problem. So the problem is given an n by d matrix A and a desired rank parameter k. Find the best rank k matrix A sub k, which minimizes the distance to A. And by distance, I mean the squared Frobenius norm, which is the sum of the squares of the entries of the matrix. So this problem has tons of motivation, for example, in machine learning and computer vision. So one of the key motivations for this problem is that it gives data compression. So if you have an n by d matrix A, then it requires nd entries. But if you factorize it as a rank k matrix, then that rank k matrix can be written as an n by k matrix multiplied by a k by d matrix. So that'll end up requiring nk plus kd entries instead of nk. And this data compression property also leads to faster multiplication when you're multiplying a matrix by a vector. So this version of the problem can be solved exactly in polynomial time. But we'll instead be focusing on a different version of the problem. So again, we have a matrix A, and we want to find a good rank k matrix A sub k, which is close to A. But this time, the definition of close we'll be using is the entry-wise L1 norm. So the L1 norm of a matrix is the sum of the absolute values of the entries of that matrix. So why are we studying this problem? So the key benefit of this objective compared to the Frobenius norm objective is that it's robust to outliers. So if there are some entries with large differences between A sub k and A, then this new L1 norm objective won't give so much importance to those outliers as opposed to the Frobenius norm, which will square those distances and inflate their importance. And this robustness property leads to some significant improvements in computer vision and signal processing problems. So let me just give an example of that robustness to outliers property. Here, if you have this example matrix is an n by n matrix. So in the top left corner, you have an entry of n, and in the bottom right corner, you have, in the bottom right submatrix, consists of all ones. Here, intuitively, you should think of this row as being an outlier and the rest being sort of the standard entries of the matrix. So what is the optimal rank 1 solution? Well, in the L2 norm, it'll just consist of this top row. And while in the L1 norm, it'll just consist of these rows with this entry zeroed out. So why is that? Because in the L2 norm, the error obtained when using this matrix, when using this row to span the factorization, is n minus 1 squared, because this submatrix has n minus 1 squared entries. Well, if you use these rows, then the error incurred on this row is n squared. So more importance is given to this outlier. Whereas in the L1 norm, if you leave out this row, the error is only n. So that's why the L1 solution will choose each of these rows. So unfortunately, this problem is NP hard because now we're dealing with absolute values instead of squares. So we lose the nice algebraic properties. And in fact, even obtaining 1 plus epsilon approximation for L1 low rank approximation is hard. And we'll also be considering the variant of this problem called LP low rank approximation. So instead of the L1 norm, we'll consider the LP norm. And even getting an O1 approximation for that problem is NP hard if you assume like a recent complexity conjecture known as the small set expansion hypothesis. So because of that, we'll be making a compromise. So we'll accept by criteria algorithms. So what I mean by that is if you have a matrix with n rows and d columns, and you have a desired rank parameter k, then instead of returning a matrix of rank at most k, you're allowed to return a matrix of rank at most r, where r is slightly larger than k. So r can be something like k log k or k log d even. And this is a typically accepted compromise in a lot of dimensionality reduction problems like clustering, k-means, k-median, and different versions of low-rank approximation. Okay, so before I go to the algorithms, let me just give some definitions. So your opt sub ak is the optimal rank k error for A. So distance between A and the optimal A rank k matrix A sub k in the L1 norm. And also, if you have an n by d matrix A and a subset of column indices, because they're d columns, then A sub S is the subset of columns of A whose indices are in S. Okay. So now we'll get to the algorithms, and feel free to stop me if you have any questions. So we'll be studying a class of algorithms known as column subset selection algorithms. So those algorithms are as follows. So first, the algorithm will select a subset of columns of our input matrix, and there are many ways to do that. And then once we have that subset of columns, we will use that subset of columns to span our low rank approximation. So here the low rank approximation is in the span of U, which is a subset of columns of A. So why will we restrict attention to such algorithms? So there are many motivations. So the main motivation is that column subset selection allows you to basically select a set of features in the input matrix. So if you have a data set, for example, then for each example in the data set, you're selecting a small number of features which explain all of the other features in the data set. And because you can relate the column subset to the original matrix, this makes this more easy to understand for humans compared to, for example, an arbitrary low rank approximation. So that's the advantage of these algorithms. So that is why these algorithms have been studied for many loss functions. And one interesting question is how well do column subset selection algorithms do compared to the best low rank approximation? So what approximation factor can they obtain? And so we'll also be looking at LP low rank approximation, as I mentioned before. So instead of the L1 norm, a more general problem is if you measure the distance in the LP norm. So the sum of the p powers of the absolute values rather than the sum of the absolute values. So for LP low rank approximation, how does column subset selection perform? So when p is equal to 2, you can actually get a very good approximation. You can get a 1 plus epsilon approximation with a small number of columns, like essentially k columns up to log factors. And unfortunately, when p is greater than 2, then a recent paper shows that the best you can do is k to the 1 minus 1 over p. So that's a tight upper and lower bound. So the best column subset selection in the worst case can get an approximation factor of k to the 1 minus 1 over p. But the case when p is at least 1 and less than 2 is not fully resolved. So we'll set out to find out what the optimal polynomial time achievable approximation factor is. So first, a lower bound for L1 column subset selection is that no column subset of size poly k gets an approximation factor better than square root of k. So even if you select poly k columns of your input matrix and get a low rank approximation spanned by those columns, you still cannot get an approximation factor that's better than square root k. The square root k is the lower bound. So let's look at a couple of the well-known upper bounds. So first, let's look at some exponential time algorithms. So one exponential time algorithm gets an O of k approximation. And around the same time, another exponential time algorithm, which tries all subsets of k log k columns, gets an O of square root k approximation. So this is tight, but it's exponential time. And then there have been several polynomial time algorithms in recent years, and they've all gotten O of k approximation for L1 low rank approximation up to log factors. So now in our work, we show that by modifying those algorithms, we can get an O of square root k approximation up to log factors. And we show that the lower bound can be achieved in polynomial time. So how do we do this? So our algorithm is based on an algorithm which has been studied in these 3 recent papers. So let me just give an overview of that algorithm first from this previous work. So the way this algorithm for selecting columns works is if you have an n by d matrix and a desired rank, then to select a good subset of columns, you first sample 2k columns uniformly at random. And out of all the remaining columns, you try to fit all of them using this random subset of columns. And you look at the error that you obtain for all of those columns, and you take a constant fraction of those having the best error. And you say that those columns are okay, that they've been covered pretty well by this subset, and you just get rid of them. So you consider them to be covered and you don't deal with them anymore. And so now you've reduced the number of columns left by a constant fraction. So now you apply the same algorithm for the remaining matrix. And ultimately, you, as your ultimate column subset, you return the union of all of these column subsets which you've sampled randomly. So let me just illustrate how this algorithm works in pictures. So here you have your matrix. And now from that matrix, you sample 2k columns uniformly at random. So here is your uniformly random subset of columns. And here are all the remaining columns. So for each of these columns, you try to fit it using this subset of columns. So you perform L1 regression on each of these columns using this subset of columns. And now out of all of these columns, take the constant fraction of those columns, which has the lowest error, right? And you group all of those columns together over here. And you consider all of those columns to be covered. So they're gone now. And you will include this in your ultimate column subset. So these uniformly random columns. And then you run the algorithm on this remaining matrix A prime. So A prime is the columns which have not yet been covered. And then you get a subset from A prime, and you combine that subset with this subset to get your final subset. And how does the analysis of this algorithm work? So the first, so let me just summarize the key observations from these previous works. So first, observe that the uniformly random subset Si together with another uniformly random column of A. So we just, out of all the remaining columns, we just look at a uniformly random column. And we say that together, they form a uniformly random subset of A. Now, how well is A sub t covered by the rest of the columns in this large uniformly random subset? So let B be the combined subset, then B has a subset of K columns spanning an O of K approximation to the optimum on B. So to get that subset of columns of B, what you do is you first take the optimal rank K approximation to B, so U star times V star. And then you look at V star. V star is a K by D matrix. So you take the it's a K by, sorry, B has 2K plus 1 column. So V star is a K by 2K plus 1 matrix. And you look at the subset of K columns of V star, which have the largest determinant. And then you take those indices in B and use them to span an O of K approximation to B. So then that's a subset of B of K columns. So this new column A sub T is a uniformly random column of B, which has 2K plus 1 columns. And the optimal max determinant subset of B has K columns. So A sub T has probability at least a half of not being in that max determinant subset. So it's covered well by the rest of the columns of B. So with that, we have this lemma. So in these previous works, they showed that for uniformly random column A sub T, with good probability, it's covered up to an O of K factor by the uniformly random subset that is sampled. And then, so it holds for each of these columns, it holds with constant probability, and use that to show that for a constant fraction of columns, it holds with constant probability again. So now each of those columns are discarded, so that constant fraction of columns is removed, because each of them is covered well up to an O of K approximation factor. So O of K times the optimum and divided by D, because each of those columns are uniformly random. So each of those columns are discarded. And what is the cost on each of those columns? So you sum up the costs over each of those discarded columns. And the number of discarded columns is a constant times D, right? And the cost on each of those columns is O of K times the optimum on A divided by D. So that's O of K times the optimum on D. And now we've removed a constant fraction of columns. So the number of times we have to repeat this is O of log D, because each time it decreases by a constant fraction. So the number of columns will be 0 after log D iterations. So all columns will be covered. And the total cost is the cost on each iteration times the number of iterations log D. So K log D times the optimum. And the log D can be replaced with log K using a more refined version of this analysis. So based on previous work, there is an O of K log K approximation. So how can this be made into an O of square root K approximation up to maybe some log factors? So to do that, we need to choose the best column subset for B. So remember that B is the uniformly random subset that we sample together with another column. So what is the best subset of B, which has a high chance of covering any other uniformly random column? So in those previous works, they took the max determinant subset and said that this is within an O of k factor of optimal. But for the L1 norm, this is not the best column subset, because intuitively, this max determinant subset covers the other columns by spanning it with a linear combination where all of the coefficients have norm 1, and the number of vectors in the linear combination is k. So by the triangle inequality, this gives an O of k factor of optimal error. But it's not clear how this argument can be improved. So instead, we look at a different notion of the best column subset. So once we sample B, we need to find out what is the best subset of B that we use to cover another column. So to do this, the first tool that we use is sampling by Lewis weights. So here, let me just give a short overview of this. So given a matrix, you can sample a subset of columns of A and then reweight those columns appropriately. So now when you multiply this reweighted subset by any row vector, then the norm is approximately the same as if you multiplied the original matrix by that row vector. So already you can see that this subset is appropriate for L1. And in fact, this result is what was used to show the existence of a column subset which spans an O of square root k log k approximation. So in work by Song, Woodruff, and Zhang, it was shown that if you're given a matrix A and a desired rank K, then using essentially the same distribution on weighted column subsets of A, by sampling columns from A according to this distribution on subsets, you can get an O of square root k log k approximation to the optimal. So here the size of this subset is O of k log k, because here the size of this random subset is d up to log factors, where d is the number of columns. So where does this square root k log k come from, right? Because here you had 1 plus epsilon. So let's see why this square root k log k approximation comes about. So let me quickly go through the proof from this work. So if U star V star is the optimal rank k approximation for A, then so S is the Lewis weights distribution on subsets of V star. So here V star is the right factor. So you sample column subsets of V star. So here V star S is a random subset of V star, and A sub S is the corresponding random subset of A. So you sample those same indices in V star and A. Now you can show that, so here is the L1 rank K objective, right? And so here's the original goal. So find a rank K matrix which is close to A. So in this previous work, it was shown that instead, if you just look at the subset indexed by S, then you can just take the subset of columns and then find the corresponding left factor. And you only lose an O of 1 factor. So that gives you an O of 1 approximation. So you just want to find a U minimizing this. So here I didn't do anything new here. I just observed that the L1 norm of this difference is the sum of the L1 norms on the rows, on each of the rows. But now we make an observation, which is that, so the number of columns selected by this random subset is O of k log k, right? So we can in fact switch this to the L2 norm. So what happens to the error when we do that? So what is the relationship between the L1 norm and the L2 norm? So for any vector with n coordinates, then the L1 norm of that vector is within a square root n factor of the L2 norm of that vector, right? So what is the dimension of each of these row vectors? So recall that there are S columns in the subset. I mean, there are O of k log k columns in this subset S, meaning each of these row vectors has dimension O of k log k. So by switching to the L2 norm, we get a distortion of O of square root k log k. And so that's where the O of square root k log k distortion comes from. So we just need to make sure that when we solve this L2 objective, the left factor U it gives us a column subset. But when we are, how do we find the solution to this L2 problem? Well, we can multiply on the right by the pseudo inverse of this matrix. So that's the standard formula for least squares regression. And by combining the solutions for each of the rows, we find that U is equal to this column subset of S, column subset of A, plus some pseudo inverse of some matrix.
Hey, can I ask a question?
Yes.
Okay, can you explain why it suffices to restrict to the subset of columns if we selected by Lewis weights to get an O of 1 approximation? This computation is in
Okay. Okay, so this, are you asking about this observation? Mm-hmm. Okay, so I guess I won't go too much into the details, but a quick sketch is that, so to show this, the main observation is that when you select that subset of columns S, you're multiplying on the right by a sampling and rescaling matrix S. And you can show that when you multiply by a sampling and rescaling matrix, then it increases the norm by an O of 1 factor due to Markov's inequality. Mm-hmm. So that's for the upper bound. And then for the lower bound, so you can subtract off this term, and this is due to, this comes from Markov's inequality. And then I guess a one-line explanation for this is that, so here you have this subspace embedding property. So basically, if you multiply on the right by this sampling and rescaling matrix S, then that gives you a subspace approximation, I mean, subspace embedding for the row space of this matrix A, right? Mm-hmm. So here, what it's doing is it's giving you a subspace embedding for the row space of V star. And that's what allows you to conclude that you only lose an O of 1 factor when you replace it with this subset. Does that make sense? Mm-hmm. Thanks. Oh, yep, of course. Yeah. So by taking this column subset A sub S, then so we saw that we lose an O of square root k log k approximation factor. So that is the optimal subset that we should be using. So what does this result tell us? So this result tells us that there's a distribution on random subsets, which gives an O of square root k log k approximation. But all we need from this is the fact that there exists a subset which gives an O of square root k log k approximation, right? Because it holds with constant probability, so one subset exists. Yeah, so in this paper, they observed that you could just try all subsets of size O of k log k, and you find one subset, and that gives us square root k log k approximation. So we're looking for polynomial time algorithms, so that's no good. But instead, we can just sample O of k log k columns repeatedly. So in the sampling algorithm from those previous papers I mentioned, they sampled 2k columns per iteration, and instead we sample O of k log k columns per iteration. So now this large matrix, so once you sample a uniformly random subset of columns and you look at another uniformly random column of the original matrix, then this big matrix has a subset of size O of k log k, which spans an O of square root k log k approximation to the optimum on this matrix. So that is why for this uniformly random column A sub t, you get an O of square root k log k error times the optimum divided by d. So now, because we're using this improved existence result from this previous paper, instead of O of k over here, we have O of square root k log k. And now you can apply a similar analysis, right? So this is what we did to obtain our O of square root k approximation factor. So in this analysis, we observed that this property holds for a constant fraction of columns. So you fit omega d columns again, and the total cost on all those columns is the d cancels out over here. So you get O of square root k log k times the optimum with constant probability and good probability. And again, you do this same thing for log d rounds. So fit a constant fraction of columns, discard them, sample, fit a constant fraction of columns, and then the total cost is this times the number of rounds, which is log d. And so, so that's the basic analysis. So the overall cost is square root k log k times log d times the optimum. So this algorithm is definitely polynomial running time. And finally, if you want to get rid of this log d approximation factor, then you can use a technique that was used in this previous work to replace that log d with log k. So this is just a more refined version of the analysis which I gave. So in this previous paper, they improved the approximation factor from k log d to k log k. And by using their analysis, we can improve the approximation factor from root k log d to root k log k times log k. So that is our polynomial time column subset selection algorithm, which gets an approximation factor of essentially root k up to log factors. Okay, so that's all well and good. So that's a tight factor for column subset selection because of the lower bound, which was previously known that you can get a better than square root k approximation factor for a column subset selection. So now the question arises, what if you want a very small approximation factor? So what if you want a 1 plus epsilon approximation or an O of 1 approximation? So what is the most efficient algorithm for doing this? So recall that there are some hardness results. So the problem is NP hard to solve exactly, and getting 1 plus epsilon approximation requires time that's exponential in 1 over epsilon. And then in this recent paper on PTASs for L1 and LP low rank approximation, it was shown that for LP low rank approximation, for P between 1 and 2, exponential time in K is also required. And this P can be arbitrarily close to 1 here. So this can even be taken as evidence that L1 low rank approximation requires that much time. So those are the lower bounds, and the upper bounds that are known are, there's a gap between the lower bounds and the upper bounds. So if you accept by criteria rank 3K, then you can get a 1 plus epsilon approximation in n to the poly k over epsilon running time. So then the question arises, are either of these tight, the lower bounds or the upper bounds? So we get an algorithm which is closer to the lower bounds. So we show that, again, we can get a by criteria rank 3K, and we can get 1 plus epsilon approximation. But now the running time is 2 to the poly k over epsilon plus poly nd. So here it's finally FPT. So here, if k is slightly larger than constant, it's not polynomial time. Whereas here now, if k is slightly larger than constant, then it is polynomial time. So if k is, for example, log to some constant power.
Is it important that the bicriteria algorithm is 3K? And anything less 1, right?
So actually in this paper, they give an algorithm which outputs a matrix of rank exactly k. But the issue with that algorithm is that it makes bit complexity assumptions. So in order to get rid of those bit complexity assumptions, what they do is first they take a crude initialization of rank k and subtract it off. So now in order to recover the optimal error, you need to find the best rank 2k matrix for that. And then when you add the rank 2k matrix with the rank k matrix, then the rank becomes 3k.
Sure, that makes sense. Thanks.
Yep. Okay, so how do we do this? So the first step, which actually, as I just mentioned, is to reduce to this new problem. So now given an n by d matrix and a desired rank k, instead of finding a matrix with rank at most 3k, we want to find a matrix B which of rank at most k, which achieves error of 1 plus epsilon times the optimum plus some additive error. So epsilon over poly k times the L1 norm of A. So we can efficiently reduce to this using some techniques from previous work, which I guess is a bit technical, so I'll skip it in this talk. So how do we achieve this? So first, a quick definition. So for a vector V, the median of that vector is the median of the absolute values of the entries of that vector. And then for an n by d matrix, the median of that matrix is the sum of the medians of the columns of that matrix. So the main tool we'll use to get FPT runtime is a dimensionality reduction technique known as a one-sided affine embedding. So if A is your input matrix, and let's just let U be some fixed left factor, then there's an oblivious sketching matrix S, so a random matrix whose distribution does not depend on U or A, with poly k over epsilon rows. And if you multiply UV minus A for any right factor V by the random matrix S, and then you take the median of this matrix, then this does not shrink the error too much. So you only lose a 1 minus epsilon factor. And if you plug in the optimal right factor, then this does not expand error too much, only by a 1 plus epsilon factor. So that is why we can just switch to the problem of minimizing this. So instead of minimizing the L1 norm of UV minus A, we minimize the median of SUV minus SA. So right, here's our goal. So let's just assume for a second that we already know U star. Then the goal is to find a right factor V, which minimizes the median of SU star V minus SA. And as we mentioned here, this decomposes across the columns. So here it's the sum of the errors on all the columns. So here's just a picture of this. So vi is a k-dimensional vector, and we want to find it so that it minimizes. Usually we would want to minimize the L1 error, but instead we multiply the oblivious sketching matrix S and then minimize the median error. And yeah. So how do we do this? I said assume that we know U star. So in order to know U star, we'll just guess SU star by brute force. And then once we do that, we'll find a suitable V. So for the first step, how do we guess SU star? Because SU star is a real valued matrix, so there are infinitely many possible entries. So instead, we'll just guess a discretized version of SU star. So here we'll say M is a discretized version of SU star, so it's approximately equal to SU star. And then once we find M, then we'll find an appropriate VI. So there's a potential issue here, which is that the running time of guessing this SU star could be very large. So what we do is we assume the entries of SU star are rounded to the nearest power of 1 plus 1 over poly k over epsilon. So we guess all of the powers of this. And we guess all powers of this quantity that are between the L1 norm of A and the L1 norm of A divided by poly k over epsilon. And the number of possible distinct entries of SU star is therefore poly k over epsilon, because all of the possible entries of this rounded matrix M are between this, and we guess in powers of 1 plus 1 over poly k over epsilon. So the number of possible entries is poly k over epsilon. And what are the dimensions of SU star? Well, S has poly k over epsilon rows, and U star has k columns. So the number of entries is poly k over epsilon, and for each of those entries, we guess poly k over epsilon values. So the number of guesses is poly k over epsilon to the poly k over epsilon, which is 2 to the poly k over epsilon. So one technical issue here, which we won't go into the details of, is when you do this rounding, you don't want the error to increase by too much. So here's a technical lemma which we showed in our full paper. So that's where the details are, which is that SU star is the original matrix and M is the discretized version of that matrix. So then if you replace SU star in our objective with M, then the error does not change by too much. So it only changes by this additive error, which recall that we're fine with this additive error. So we can just replace SU star with the rounded version. And then there's one important condition, which is that the L1 norm of the right factor V has to be at most poly k over epsilon. And intuitively think of this as being because if the L1 norm of V was too large, then that's going to blow up the rounding error between M and SU star. So we don't want to amplify the rounding error, so we'll just we'll add the constraint that the L1 norm of V is at most poly k over epsilon. So now we have a new problem. So M is the discretized SU star, and V is the right factor. And we have the constraint that the L1 norm of V has to be at most poly k over epsilon. And in the objective here, we now replaced SU star with M. So this actually turns out to be non-trivial to enforce this constraint, because, so first of all, each of these individual problems decomposes across the columns. So, and each of these problems can be, each of these quantities can be minimized separately in FPT time, because M is a poly k over epsilon by k matrix, Vj has k entries, S times A sub j has poly k over epsilon entries. But these errors are no longer decoupled, because this constraint includes information from all the columns. So it's a sum of all the entries in the right factor, right? So it's not so easy to just solve these objectives separately. So let's just, so let's see how we can actually do this efficiently in FPT time. So one simplification we can make for, first of all, is that we don't have to actually minimize this. Instead, we can just add the constraint that it's at most 1 plus O of epsilon times the optimum, along with some additive error, right? So that's just a small simplification because remember that we're okay with this additive error. Okay, so now how will we actually find the V sub j? So we will still decompose the problem across columns because that's the only way we know how to get FPT time. So for each of the columns, we'll first of all minimize the norm of that column. And we'll also add a constraint so that this quantity is not too large. So this median-based quantity is at most Cj for some cost-bound Cj, which we now have to find. What should that cost-bound Cj be? So here I'm just restating the problem. So we're minimizing the norm and adding a constraint to ensure that the cost is not too large. So ideally, we want the cost bound to be equal to the median-based cost, which we incur when this is the optimal right factor, right? Because one technical observation which we can make is that the norm of the optimal right factor is poly k, and this is due to the existence of well-conditioned bases, which is shown in previous work. So we can assume without loss of generality that the L1 norm of the optimal right factor is at most poly k. So that's why it's valid to use that as the cost bound. But we don't actually know V star. So we don't actually know this quantity, but we can just guess all powers of 1 plus epsilon, and we'll get within a 1 plus epsilon factor of this. So we try for the cost bound C sub I, we try all integer powers of 1 plus epsilon, and between this upper bound and this lower bound, and one of those powers will be within a 1 plus epsilon factor of this error obtained from V star. So what are these upper bounds and lower bounds? This upper bound is simply a crude approximation, which is that the median-based objective when you plug in V star is at most the norm of A times a constant factor. But for the lower bound, so we can't go arbitrarily low for C sub I because we must guess only finitely many powers of 1 plus epsilon. But we don't have to go lower than this, because even if the median-based cost of V sub I is here, even if this cost is equal to the norm of A times 1 over D times 1 over poly k over epsilon, if we sum that across all of the columns, then the D just cancels out with this D here, right? So we'll just end up getting some more additive error of the norm of A times 1 over poly k over epsilon, which is acceptable for us. So for this C sub I, we just guess several different powers of 1 plus epsilon. But that brings us to a new problem. So for each of these columns, there are several possible cost bounds. And for each of, so we have to guess which cost bound is correct, because we can solve this problem, certainly, for each possible cost bound. But then for each column, we need to figure out which cost bound is actually correct. Because if we go too low for each cost bound, then we might end up getting a very big norm. And if we go too high, then we end up getting a very large error. So we have to figure out which one is right for each column. So let me know if any part of this doesn't make sense. So for each column, how do we figure out the right cost bound? Well, one way to do it is by brute force. So for each column, you try every possible cost bound. And there are D columns, so this will be exponential in D, and that's no good. But another approach is to write the brute force as an integer linear program. So here, by that, what I mean is for each column and each cost bound, you create a variable. So x sub 1 and c superscript 1 will correspond to the first column and the first cost bound. And it'll be a 0, 1 valued variable. So 0 if that cost bound is chosen, and 1 if it's chosen, 0 if it's not. So we'll add 2 constraints, 1 for the median based cost, 1 for the norm, and then we'll also add a constraint that exactly 1 is chosen for each column. So that also cannot be done in polynomial time, but now that we have an integer linear program, we can just take the LP relaxation. So instead of the variables being 0, 1 valued, we say that the variables are allowed to be between 0 and 1. So we solve the linear program corresponding to those variables. And so that can be done in polynomial time, but the problem is that we don't actually have an assignment. So it's because those can be fractional. But we can recover an assignment. How do we do that? Well, observe that in each column, only one cost bound can be chosen, right? So in the integer linear program, we write that constraint by saying that the sum of all the variables in each column is at most 1. But what does that mean? That means now when we look at the fractional solution, then that fractional solution gives a probability distribution for each column over all of these cost bounds, right? So for each column, we can just sample a cost bound according to that distribution. And with good enough probability, we know that both the cost constraints and the norm constraint are met. Because why do we know that? First of all, the median-based cost constraint can be written as a linear constraint. And second of all, the norm constraint can also be written as a linear constraint. And by linear, I mean linear in those variables. So in expectation, the total median-based cost and the total norm are at most what we want them to be. So in expectation, the norm is poly k, and in expectation, the median-based cost is 1 plus epsilon times the optimal plus some additive error. And by Markov's inequality, this holds with the probability epsilon, and then we can sample multiple times to boost this to constant probability. So here, so in summary, we solve the LP relaxation of that brute force integer linear program, and then we get an actual integer valued assignment by just sampling from this fractional solution. So in summary, let me just quickly recap this algorithm. So here, S is the oblivious sketching matrix. So each of its entries are Cauchy random variables as an aside. So S is the sketching matrix, and U star is the optimal left factor. So we guess a discretized version of SU star, whose entries are all powers of 1 plus 1 over poly k over epsilon. And M is the discretized version. So we wanted to find a right factor V. so that it minimizes this new version of the median-based objective. So instead of SU star, we have M here, and we want to minimize median of MV minus SA. And we also want the norm of V to be at most poly K. And finally, once we find a good right factor V, we can just find the best left factor for that V using linear programming. And in fact, if you had U star over here and you had the V from before, then this is within a 1 plus epsilon factor of optimal plus that additive error. And you can only do better by solving the best factor for V using linear programming. And that's it. That's your low rank factorization. So let's just go through the runtime of this algorithm. So as we mentioned before, the number of guesses is 2 to the poly k over epsilon. And to solve this optimization problem efficiently, we need to first solve a bunch of smaller median-based optimization problems. So each of those median-based optimization problems can also be solved in FPT time, because here the matrices we're dealing with only have poly k over epsilon entries and variables. So that's 2 to the poly k over epsilon. And then there are polynomially many such small problems. And then to solve the LP relaxation is polynomial time. And this is just an L1 regression problem. So it can be solved through linear programming, which also takes polynomial time. And overall, the algorithm is 2 to the poly k over epsilon times polynomial in ND time. And that's the same as 2 to the poly k over epsilon plus poly ND time. So that's it. That's our PTAS. And are there any questions?
Hey, Arvind, can you hear me?
Yes.
Hi, so thanks for the talk. Actually, I'm an author of one of the paper you mentioned here, the DWC19 paper.
Oh, wow.
Yeah, and I think the focus of our work and your work is kind of different because you are focused, if I understood correctly, you are focusing more on the bi-criteria algorithm for the column subset selection problem.
Yes.
And ours was more on the exact rank algorithms.
I see.
Yeah, so so that being said, I have 2 questions for you. So the first one is about the L1 low rank approximation.
Okay.
If we consider only exact rank algorithm, there is still a gap between the upper and lower bounds. I think the lower bound is square root of k,
Yes.
and the upper bound is O of k. So do you think it's more likely to be O of k or O square root of k, or?
That's a very good question. So I'm not actually sure of the answer to that. So right now, even an existence result for exactly k columns is not known. So
Right.
I don't know what it would be.
Yeah, and so I think the other question is that I don't think in our paper we established any kind of lower bound for bi-criteria algorithm for other p.
Okay.
So can you apply your algorithmic technique for other values of p's? For example, p is larger than 1 and smaller than 2. Can you get some kind of bound on the bi-criteria approximation factors?
It might be possible. So the thing is that this algorithm relies on the Lewis weights.
Yeah.
So Lewis weights exist not only for p between 1 and 2, but also for higher values of p. But I think the number of sampled columns might be larger for those. So recall that here for p for L1, and also this is also true for LP for p between 1 and 2. The number of sampled columns is essentially d up to some log factors. So I'll have to double check this, but for higher values of p, I think more columns may be required. But actually, maybe I can just check this now. So I can just see if,
Yeah, I mean, that grows as d to the p over 2.
okay.
Yeah.
Okay, so then, yeah, the main problem with using LP Lewis weights is that the number of columns is now too large. So when we switch to the L2 norm over here, then the distortion is square root of n, which is it'll be too big.
So for what values p? So the number of columns needed is d to the power of p over 2, right? So if p is less than 2, is it a big issue?
So if P is,
It's d. Yeah, I mean, that's for p greater or equal to 2. Like, I mean, it's always at least d.
Oh, I see.
Does that make sense?
Yeah.
Okay.
Yeah, are there any more questions? Okay, let's unmute and clap for our speaker. Yeah, thanks very much, Arvind.
thank you for having me.
Yeah.